concavity and point of inflection. The graph of a definition, the graph of the differential function y equal f of x is concave f on an open interval I if f prime is increasing on I. So what does it mean by f prime increasing? F prime increasing on I, this means when f double prime is greater than 0 on the interval I. Concave down on an open interval I if f prime is decreasing on I. Decreasing on I means f double prime is less than 0 on the interval. So concave up means when the curve is open up this way, concave down like that. So let y equal f of x be twice differentiable on the function interval I, and like we said, f double prime greater than on 0 on I, the graph of f is over I is concave up, otherwise it's concave down. A point C, f of C, where the graph of a function have a tangent line and where the concavity change is the point of inflection. Okay. At the point of inflection, either f double prime equal to 0 or f double prime does not exist. So here we have situation where the graph is concave up and concave down. We can concave up and decreasing, concave down, concave up decreasing, and concave up increasing. So there's different situation. And in the other graph, we have an inflection point. Okay? So second derivative test for extrema. Suppose that f double prime is continuous on an open interval that contains x equals c. F prime of c equals 0 and f double prime of c is less than 0, then f have a local maximum at c. Okay. Similarly, you have local minimum, and we have and if f prime and f double prime both equal 0, then the test fails. The function f may have a local maximum and local minimum or neither, so we have to check for those. Now let's take a look at how to solve this type of problem. Sketch the graph of f of x. Identify the domain of f, x, and y-intercept, and any symmetry the graph may have. So you try to list out all the information that you know about the graph. What do you know about it, right? So find the first and second derivative, find a critical point of f, if any, and identify the function behavior at each one. Find where the curve is increasing and decreasing. Find the point of inflection, if any occurred, and determine the concavity of the curve. Identify any asymptote that may exist. Plot some key points so that the intercept and the point found in step 3 to 5, and sketch the curve together with any asymptote that exists. Let's take a look at the graph of y equal x to the 4th minus 2x squared. So first of all, if f of x equal to x to the 4 minus 2x squared, this graph is continuous on its domain that is negative infinity to infinity, then no asymptote. Let's take a look at what is the x-intercept. The x-intercept is the value of x with y equal to 0. So set this equal to 0 and solve for x. So we have x equals 0 and x equals plus or minus root 2. So let's put the x-intercept onto the graph. So here's where root 2 is, estimately, and root 2 and negative root 2. And let's find the y-intercept. Y-intercept is the value of y when x equal to 0. So y-intercept is 0, 0. So let's put our y-intercept here. The next thing we do is to find the increasing and decreasing interval of the graph. First, we'll find the critical value by first taking the derivative of f of x. Set that equal to 0. So the critical value x equal to 0 plus or minus 1. We will make the table to determine the increasing and decreasing interval. So the interval that we're looking at is from 0 to negative 1, from negative infinity to negative 1, from negative 1 to 0, from 0 to 1, from 1 to infinity. Let's take a look at the side of each of the factor of f prime of x. So here we have 4x, x squared minus 1 is f prime of x. Okay, in this interval, 4x being negative, then positive. So f prime is negative, 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 make it positive, positive, negative, let's make negative, positive, positive, let's make positive. So f prime of x is increasing in the interval of negative 1 to 0 and from negative 1 to infinity, decreasing from the interval of negative infinity to negative 1, and from negative 1, and from 0 to 1. So let's plot the critical point onto our graph. So here we have negative 1, 0, and 1. So this looks like we have a local min at x equal to negative 1. F of negative 1 is equal to negative 1 to the 4th minus, or is it plus? That is minus 2 times negative 1 squared. That is 1 minus 2, that is negative 1. Again, we also have a local min at x equal to 1. F of 1 equal 1 to the 4 minus 2 times 1 to the 2nd. So this is also negative 1. So here we have a local min at negative 1. So these are the 2 points that we have a local min. We have a local max at x equal 0. Local max. X equals 0 and f of 0 equal to 0. So here we have this point. So far that's what we have. Okay. Now we need to find the concave interval. So to find the concave interval, we first need to take the second derivative and do the second derivative test. So f prime of x is equal to 4x to the third minus 4x. So then f double prime of x equal 12x squared minus 4. We let f double prime equal to 0. So 12x squared minus 4 equal to 0. X squared equal to 1/3. So x equal to plus or minus 1 over root 3. And we will approximate this to be plus or minus 0.57. So let's take a look at the concave interval. So we look at the interval from negative infinity to negative 0.57, from negative 0.57 to 0.57, and 0.57 to infinity. Okay. And we will use the test value. So when do we use test value? We use test value when we can't really tell exactly what is the sign of each of the factors of the function that in question. So if you can use the each of the component of the function, like for example in the finding the increasing and decreasing interval, I was able to use the component of the function to find out the sign of it, right? To find out whether it is positive or negative. I can't really do the same here without much of a guess and check. So I'll just go ahead and use my test value. Let you test value x equal to negative 1 here, x equal to, and we ideally does not want to use a value that already appeared in the previous table. So for example, in this case, I don't want to use 0. Okay, so we use say 0.2 for instance, and here x equal to 1. When I check the sign for this, I really don't care about the value of the function. I only care about whether it is greater than or less than 0. This is positive here, this is negative, and this is positive. So this is increasing concave up in this interval, increasing concave up, decreasing concave down, and this is concave down in this interval. So what I can say, this is concave up, concave down, and here concave up. Right? So what happened here, and let's find the value at x equal to negative 0.57 and at x equal to 0.57, because these are where the concave change. These are our inflection point. We evaluate f of negative 0.57. This is about negative 0.57. F of negative 0.57 is the same as positive, negative 0.57. Okay, so we can plot this onto our graph. Okay, so this must be our inflection point. It change from concave up to concave down. That's the idea. All right. So here, what do we have together? We have that the function is decreasing from negative infinity to negative 1, and that it is concave up. Okay, so negative infinity to negative 1, and it passed to that y-intercept, and it's concave up. At the inflection point, negative 0.57 to negative 0.57, now we have a concave down, and then it changed to a concave up again, and then increasing. So this is the shape of our graph. Okay. Let's go try this again. Let's get the graph of 2x squared divided by x squared minus 1. we first need to identify all our asymptotes, our x and y intercept, and let's try to have an idea about the behavior of the graph. Okay. So the domain of this graph, the domain here is from negative infinity to negative 1, union with negative 1 to 1, union with 1 to infinity. So the graph f of x has vertical asymptote at x equal to negative 1 and at x equal 1. So let's put in our vertical asymptote for each of this case. And I will make it a dashed line. Okay. And we have the horizontal asymptote y equal to 0. So let's put in the horizontal asymptote. Excuse me, the horizontal asymptote in this case is y equal 2, right? The horizontal asymptote here is y equal 2. So let's put in the horizontal asymptote. Let's find the x and y intercept. X intercept, well, 2x squared equal to 0. That implies x equals 0. Y-intercept, the value of y when x equal to 0, that also equal to 0. So x and y-intercept are the same value, 0, 0. Now let's go ahead and find the increasing and decreasing for the function. First, we take the derivative of f of x. F prime of x equal to negative 4x divided by x squared minus 1 squared in this case. F prime of x equal to 0. Prime of x equal to 0. When x equal to 0, F prime of x is undefined at x equal plus or minus 1. So we will look at the table from interval from negative infinity to negative 1, from negative 1 to 0, from 0 to 1, and from 1 to infinity. And let's take a look at each component of the f prime of x. Negative 4x, x squared minus 1 squared. Now because x squared minus 1, and then we square it, so it's always going to be positive in this case. So this will be positive, positive, negative, and this is going to be negative. So f prime of x is positive, positive, negative, and negative, so that it increasing and then decreasing and then decreasing. This means we probably have here we have a local max at x equal to 0, f of 0 equals 0. Okay. So let's take a look at our concave. F double prime of x equal 12x squared plus 4 divided by x squared minus 1 to the third. F double prime of x equal to 0. That's not gonna happen, right? Because 12x squared plus 4 doesn't equal to 0. You solve this, then x squared equal to negative 4 over 12. That's not going to happen. But we know that f double prime of x is undefined. But x equals plus or minus 1. So the interval that we will be considered of concave is from negative infinity to negative 1, from negative 1 to 1, from 1 to infinity. And we take a look at the component of f double prime of x. So 12x squared plus 4, x squared minus 1 to the third, in this each of this interval. Then f prime double prime of x, what kind of, whether it is positive or negative in the interval that is given. So because we have 12x squared plus 4, this is always going to be positive. This be positive, negative, and positive. So here we have a concave up, concave down, and concave up. We have inflection point at negative 1 and 1. However, that is where we have the vertical asymptote. So the graph looks kind of like, so concave, from the interval from negative infinity to negative 1, we have the graph that is concave up and increasing, concave up, increasing. From negative 1 to 0, it also increasing. From negative 1 to 0, increasing, but concave down. From 0 to 1, decreasing, concave down. From positive 1 to infinity, that is decreasing, concave up. What does it mean by concave up and concave down? It means if I draw a tangent line here, for example, this curve is concave up. If I draw a tangent line, the curve is above the tangent line. Concave down, if I draw a tangent line, the curve is below the tangent line. That's what it meant by concave up and concave down, in case you have a question on that.